Hello everyone, welcome back to Think Lab by Saurabh. So in today's video, we are going to understand one of the most important architecture behind modern large language model. It's called mixture of expert, or we simply call MoE, right? So model like Mistral, DeepSeek, MoE, DBRX, and many next generation AI system use this architecture. So by end of this video, you will understand what is the MoE and why was it invented and how does it work internally and what is the router and what are the different export and why is it much faster than the traditional transformer model, right? Okay, so let's begin. So what's the problem does MoE solve, right? So that is the first important question. What problem does MoE solve, right? So before understanding MoE, we need to understand the problem with dense model, right? So traditional transformer model we call the dense model. So in dense model, every token activates every neuron inside and every feed forward network. Suppose a model has a 50 billions, right, parameter. So if you ask a questions, explain machine learning. So all 50 billions parameter participate in the computation, right? So even if only one fraction of model is actually needed, so this wasted the huge amount of computation power. So as the model become very larger, as GPU memory also increase and inference becomes slower. So training becomes more expensive here in this case, right? And scaling become very difficult. So researcher ask the simple questions. Can we build a trillion parameters model without using all the trillions parameters every time? So the answer is the mixture of export, right? So what is a mixture of export? So mixture of export is a sparse neural network architecture. So instead of using one feed forward neural network, it replaces it with many smaller feed forward network we call the export, right? So a small neural network is called router, and we are also use decide which export should be processed in each token. So only those selected export become active and remaining export stay inactive. So this is known as the sparse activation, right? So the model have contained hundreds of billions of parameters, but only a small percent of them are activated for each tokens. So there are core component of MoE, right? So there are major four component, right? First one is the input token, right? Component number one, input token. So everything start with the input token. For example, artificial intelligence, Python, each token had its own embedding vector, right? So now with the component two is the router. Okay, we are called as a network. So router is a lightweighted neural network. Its job is very simple. It's receive the hidden representation of token and then it calculate the score of every export. For example, export 1 is 0.815, export 2 is 0.15, export 3 is 0.93, export 4 is 0.45. So the router select the highest scoring export, right? So usually top one routing, and top two writing like this, okay? And now we are moving to the component 3, the export network. So each network, each export is usually as independent feed forward network. So during the training, different export naturally specialize in the different domain. For example, one expert good in mathematics, another specialize in programming, another become the better in scientific reasoning, another handle the multilingual translation. So no one is manually assigned these roles, right? So this specialization emerged automatically during the training. Now we are moving to the component 4, the output combination. So after the processing, the selected export output are combined using the weighted average based on the router probability, right? So this combined output is passed to the next transformer layer, right? So this process repeat for every token in every MoE layer, right? So if you check the complete pipeline of MoE, right, mixture of export. So let's see the complete workflow, right? The first one is the input token, another one is the embedding layer. Second one after that the self attention, right? Now we are moving to the router network, and after that we have to perform router computes a score for every export, right? And we have to select the top k export are selected, and only selected export perform the feed forward computation, right? And after that we have to check the weight and their combination. Then we move to the next transformer layer, and finally we get the prediction. So this happen independent way for every token. So different token in the same sentence may be activated different export. So why MO is faster, right? That is a very important question. So imagine a hospital with the 500 doctors. So every doctor examine every patient, right? So it is a very extremely expensive. So instead of a reception send the patient only to the required specialists, right? Like cardiologist, neurologist, orthopedic doctor. So this receptionist is the router. So doctor are the expert, right? Huh. So doctors are the expert and patient are the tokens. So this is exactly how the mixture of expert work, right? So now we are going to compare the dense versus MoE. So dense is basically transformer, right? So every parameter is active and high computation and higher GPU cost, and it's a slower inference, and we have a limited scalability. So MOU, if you're talking about the MOE transformer, so only selected expert become active. So it's also lower computation, so lower inference cost and much larger model capacity. Okay. So if you check the mathematical intuition behind all these things, suppose a model contain the 64 expert. So each expert have 2 billion parameter. So total parameters become 1 to 8 billions, right? 128 billions parameter, but the routers select only two export. So only 4 billions parameter are activated for one token, and the model behave like the 128 billions parameter model, right? So while performing the computation closer to a 4 billions model, right? So this is the power of sparse computations, right? If you check the challenges of MOE, right? So this is the MOE, not a perfect, right? There are several engineering challenges also in the mixture of export model. The first one is the load balancing. So if one export, receive the most tokens, so other export remain unused. And the second one is the export collapse. So only few export dominate the training, right? And the third one is the communication overhead. So every expert may be reside on the different GPU, so required expensive communication. So if you're talking about the fourth one, so the router is the router is unstable, right? So incorrect routing reduce the model quality. So researchers solve this issue by using the balancing losses and better routing algorithm to optimize the disturbed training, right? So if you check the real world model, by using the mixer of export, so some famous model are like Swiss transformer, Mistral is also there, DBRX is there, Deep Six is also there, right? So many modern frontier model also use this mixture of export style sparse architecture, right? So if you take the final takeaway from this video, so mixture of export is the one of the biggest innovation in modern AI. So instead of making the every neurons work, so mixture of export, intelligently activate the only export need for the task. So this enable the AI system with hundreds of billions or even the trillions of parameter while keeping the inference efficient, right? So if you want to build the understand the next generation large language model learning, so MOE is essential, right? This mixture of export is very essential for the building the advanced generation of large language model, right? So thank you for watching. If you enjoyed this video, so don't forget to like and share the subscribe the Think Lab by Saurabh. So see you in the next video with another exciting AI topic. Thank you.